This 4-layer stack up sucks. Okay, I'm being a little harsh on that one. Plenty of designs work on that one. But we're going to take a look at some 4-layer stack ups, and we're going to show you why, in my opinion, this one right here is the best. Signal, ground, ground, signal, with some power in there. Also joining us, special guest, Sylvie, who is exceptionally cute and a little camera shy. Okay, so take a look at these videos here. Recommend you watch them. But as you notice, they are kind of lengthy, but I assure you, they are well worth it. Loads of good information here. Let's go through these stack ups right now. Okay, all signal layers, 4 layers, 4 signals. Never seen it before, but this is kind of like the 4-layer version of a dense 2-layer board, where you would, by necessity, have to do this. Usually what gets messed up in a 2-layer board is in a dense 2-layer board, you don't have a ground plane. You've got ground every which where, but not really a plane. So I could foresee sacrifices having to be made to make this happen. So I don't want sacrifices. 3-layer board, or 3 signal layers on a 4-layer board. Okay, all right, kind of cool. I could foresee that being needed if you've got a cost-sensitive design. You just can't go up to 6 layers. Okay. So the way to make this work would be very fast signals here, fast rise time. Here, not so fast and really, really slow. So, and then these two, they will have to be routed orthogonally. Otherwise, you'll be causing yourself problems. And we don't want problems. Also, that's kind of a lot of thought. So design process, I already got a lot in my head. I want to keep it simple. So, but hey, if you got to optimize for cost, you do what you got to do. So I want to go to this one next. So I already see a problem here is that you want all the copper to be symmetrical between the layers. It's just easier to manufacture that way. So there is going to have to be copper fill here on this board, which, okay, yeah, you can make it work. I typically don't. Other videos have shown it's more work than benefit, and if you don't do it right, you can screw it up. I don't want to have to worry about screwing stuff up. I just want it to work. So this one is cool. Maybe you have some super sensitive signal and you want it surrounded by ground. All right. Cool. I've never had to use this one. Never seen it. So this one is my go-to. And I'll tell you why I use this one over this one. So, all right. One, I like 2 ground planes. Or instead of calling it ground, let's call it reference voltage. I want a big ass reference. Because in many of my designs, the case is plastic. So I'm thinking, okay, TVS diodes, where's that ESD gonna go? Well, it's gonna have to go to ground with a plastic case. So I want to throw big copper at it, which is what I do. So okay. Also, if you look here, so this is going to be 40 mils between these 2 layers right here. So on a 2-layer board, that's 62.5. You still want that orthogonal routing. So you would want that here. So that's another thing to think about. Also, we go into my favorite tool, Saturn PCB design. So just give you a glimpse of what we're doing. We have a trace that's 50 mils wide. It's on the external layer. There, we are saying a plane is present. For this, what we're doing, we don't care what the plane is, just as long as there is one. So I want you to look right here. Max conductor current, given this 20-degree C rise, 4.58 amps. Well, if I use that other stack up where signal and power are on the internal layer, go from 4.5 down to 3.1. So if it's just a regular signal, all right, cool, no big deal. But if I'm carrying power over it, that can make a big difference. So and then, like, hey, what if I need to actually do a polygon? Is about 200. Okay, 10.3 amps. Then about 7. Okay, what do I have to do to make an internal layer is to get this 10.3? Well, we have to go from 200 to probably about 400. So we have to double it. If it's a dense board, you're not going to be able to do that. So, no, that's more work. I want things to be more work. So that's why this is my go-to. Okay, when would I actually do this? When would I actually do this? Okay, time to market. If I need to get a design just out the door quickly, I know there's nothing crazy going on. That way I can just place components willy-nilly. Power's already taken care of, ground's already taken care of. That's fine. So, okay. So what I want to show you now is the return path for these two. I guess it would apply to this one as well. And this one. So for your regular traditional stack up with ground and power, okay, look, your signal goes here. Then return path goes here. It's got to jump between power and ground planes, and then it'll magically make its way back. So this is your normal stack up. This is going to be about a 40 mil difference. Is it better than a 2-layer, 62.5 mil layer board? Yeah. Yeah, absolutely. Is it as good as we can make it? No, we can go way further with those other stack ups. So there is a way to make this not as bad. So what you do is you place a capacitor nearby your signal via with a vias to ground and power. Okay, cool. And then technically this is making the best of that stack up. Have I ever seen this though? No. Would it survive a design review? Honestly, probably not. Not without a lot of explanation. And then all the seniors that have never seen it before will probably be like, whatever, you don't need it. Get rid of it. So also, it's gonna, I don't want to say pollute the BOM, your bill of materials, but it's gonna add to it. Dense, on a densely packed board, you may not have the opportunity to get one of these in, but maybe you can. So also, this note here, only the return energy current below 250-ish megahertz will travel through the local decoupling capacitors. All right, yeah, I can buy that. That sounds about right. But I don't want just 250-ish and below frequencies. I want all the frequencies. I don't want to have to worry about it. Because now, oh yeah, now we have to worry with this. We got to worry about our frequency content of the signal. For, return purposes. Ugh, that's a lot to do. So if we go down here, we have 2 ground planes. It's just dead simple. We go signal, return. We have a ground via nearby our signal via. That just looks beautiful. So, but Mr. Robert F here in this video, highly recommend it, has look at this in detail. He's got some fancy field solving software, which is ungodly expensive, I bet. So what's going on here? He's just got a couple connectors. Here's a signal. We got a via right there, and then he continues it back to this other connector. That's all he's doing. And he's experimenting with, oh, what do I do with the ground vias? So we go back here. No ground vias. Well, we've got some bad colors here. Look at this. Got amps per millimeter squared. So got a lot going on there. If you just put a ground via willy-nilly and don't really think about it, I mean, if you look, I mean, particularly in this area, yeah, it's better. The rest, maybe a mild improvement. No, we don't like that. If you just put one ground via next to your signal via, huge improvement, massive. So why wouldn't you do that? Nobody. So people question you about a capacitor with what we talked about previously, but nobody's going to question you about just doing a ground via next to a signal via. They're smaller, they're free, it's not going to mess up the bomb. Nobody's going to call you out on it. Maybe somebody will be like, why'd you do that? And you can just say, yeah, I watch videos that say it's best practice. And then they'll think, yeah, well, whatever. Even if it's not true, it's just a via. Sometimes you got to design for politics instead of for technical reasons. 6 ground vias right next to it, yeah, it's better, but I'd say mild improvement. For this, he went hog wild and did vias all along the traces, both sides. There's dozens, maybe 100 or so vias, I didn't count. So this is what I do for an RF trace. So if you want the ultimate, yeah, do this. Everybody's going to look at you weird unless it's for RF. So yeah, your biggest bang for your buck, 1 ground via next to there. Return currents are good. Much better than this. Signal and power are on the outside. You get better currents. You've got 2 ground planes. More metal thrown at your reference voltage. No switching reference voltages. So what's more to love? In development time, slightly more than this, because now you got to worry about power traces or, big or polypores, but it's not as bad as some of these others. So this is your biggest bang for your buck, best performance with maybe not minimal, but low effort. So I would recommend you do these in your designs. If you've got a 2-layer board that you're reviewing, what I recommend you do, and it's especially if it's causing you issues, one of the things you can do, upgrade it to a 4-layer board and then just do your inner layers as ground and just add a whole bunch of ground vias in your design. Very simple, very easy, lots of benefits to this stack up. So let me know what you think in the comments. Have a good one. Bye.